Hello, am I audible? Yeah, first of all, very sorry for the delay. Like, my computer had some issues, both uh, sharing the link and starting screen sharing. So, yeah, today's session will be a pretty short because we'll just learn a tool for our application purposes and basics of a concept we are going to use. So, yeah, uh, next. Okay, fine. What is a debugger? So most of you, or like some of you might have taken who have taken computer science in your 12th standard, have done programming in Python. So you might have came across errors. It could be syntactical errors where you forgot a bracket or a comma or something like that. Or it can be logical errors where you expected one output but you didn't get it. So that happened because you made some logical mistake while doing some of the calculations in between. So, what is debugging? Like the term literally suggests it's debugging. Bug is basically a flaw in your program or an error, kind of. So a debugger is a tool which helps you figure out those errors. In general, like one way of figuring this out is without using any other tool is say you're performing few operations on a given number in your code. Let's say the first step you're adding that number with another number, and in the second step you're multiplying, and last step you're doing something else, and you're printing it out. So suppose you didn't get the output you wanted, so you want to check in which step you made the mistake. So some people what they do is they'll just print the value of that variable after every operation which they do on it. And so that is like putting a print statement after the addition operation, then the after the multiplication, so on. And you can see that see whether the value um, um, after that operation is what you expect or not. If it's not, then you can figure out that the mistake was in that step. But then this is a very tedious task. Suppose you have multiple operations and you want to figure out the mistake. You won't be able to put all the print statements after every operation, and after you fix it, you have to remove all of them again. So this is where debugging comes into action. So as it's written, debugger is a tool used to inspect and control execution of program and diagnose the issues. In coding IDEs, like you might have heard of something called VS Code, in which you write code, and in those kind of applications, you will get debuggers for different programming languages. So what they basically do is set let you set something called breakpoints, in which um, you can halt the program at a particular place, and you can see the value of the variable which you are trying to operate on. So that's like basically stopping the program after the second operation and seeing what is the current value of the variable, or if there are multiple variables, those variables. So this is what one of the functionality a debugger offers you. Okay, so next. So yeah, today we'll be dealing with something called GDB. So GDB, which stands for new debugger, is a command line debugger for C and C++ programming languages. This was developed by a person named Richard Stallman, who is the same person who developed the compiler for C, which was GCC, and he is also which later became a part of the first Linux operating system. This compiler and the Linux kernel, which was developed by Linus Torvalds, as we saw in session 1, these were put together, and the first Linux operating system was published. Yeah, so this is basically a open source software. That means the source code of these programs are available for free on the net. Okay, so going into GDB, so uh, yeah, after you compile a C program, you'll get the executable. Now, in so for working with GDB, you can just use the command GDB followed by the name of the executable, and it will go into the GDB mode, and there you can do various operations like set breakpoints and like run the program itself and give a value, then again check the go to the next step, then again check the value, like that. Okay, yeah. So next, now we'll be looking at these commands which you can use in GDB. So as now screen sharing has become an issue, I won't be able to show the live demo of GDB. I'll see if towards the end I can show you all this, because that was a major part of the presentation and I had prepared it. I'll see at the end. So for now, I'll just explain. So what run? So run or simply putting R just runs the program, and it. So suppose if you have a line of code where you want to take an input, it just runs and it goes to that lines and asks you for the input, and you can enter it. So if you keep on like running the program, it will run towards completion. Now, yeah, so continue. So while running the program, you can in between you can just exit out of the program for the current time being, and you can look at the uh, memory of the like the memory in the stack while the program had run. Yeah, so that you can observe while just you can just stop the program there and you can see. So that also I'll show you if it's possible. So if you stop a program like that, then for continuing from where you left off, you can use the continue command. Okay, next. Okay, yeah. Now the one of the most important commands, which is break. This is used to set a breakpoint. So um you can write B followed by, now there are two options for you. Either you can specify the location of the line in your source code. That is, if you know what the source code initially was, you can just put B and the line number of the place where you want to set a breakpoint in your original code. Or the second option is, if you can see the assembly code, that also I'll show. You can disassemble the code in GDB. From there, you can see the various the assembly code lines, and that will be having some addresses. You can also put those addresses as the breakpoint. So like one line of code in your source code might correspond to 2 or 3 lines of assembly instructions in the assembly code. So you can again, within the assembly, you can put a breakpoint. And info breakpoints will give you the list of all the breakpoints you have set, and delete and the specific number of the breakpoint will delete those breakpoint. Yeah, next. Now, yeah. So the next command is n, which stands for next, and it just executes the next line in your code, like the source file of your code, like the program which you have written. So this is also similar to continue, but then you're just executing the next line alone. And NI stands for next instruction. So this is the corresponding command of next in the assembly code. So like your source code, if you give NI, it will just go to next line, next instruction in your assembly code. Yeah, next. Now step. Okay. Yeah. So step again. It's similar to next, but if there is a function called, if there is a line of code which calls another function, then it won't go to that function and it will just continue. And SI, which step instruction, then what that will do is, if there is a, oh, okay, sorry, okay, step. Okay, the difference between next and step is, if there's a function, then next doesn't go to the function. But if you put step instead of that, then it will go into the function call, which refers to another function somewhere in your program. And similarly, step instruction will go into something called a subroutine. So there is no concept of functions in assembly. Yeah, we'll see that in the next slide. Like after 2 slides, I'll explain that. Yeah, next. Okay, next command is print, which just prints value of any variable which you have, or it can also print the value stored in the current registers. So here you can see the first line is print $RSP. RSP is one of those registers which corresponds to the current stack pointer position, and yeah, print $RSP will return the memory address to which RSP points. And clear command clears the breakpoints. And info locals registers displays the value of the local variables and the current value stored in the registers. Yeah, next. Okay, now another important command is examine. So I've told you, like, in between the program, you can see the stack in which the different values will be stored. So for doing that, you can use this examine command, where you can see. So suppose you have this stack pointer, you can use the examine command to see some 20 or 30 bytes from the stack pointer. So if possible, I'll show you that to see where our variables will go when we input them. Okay, next. Yeah, okay. This was told in the last session. The how the memory happens when you run the executable, it creates a stack frame in the RAM, and yeah, also it can it yeah, it'll have the code and it'll have the variables and all those stuff in that stack. And registers are kind of memory addresses, but they're very fast and easily accessible, and they serve some special purposes, like RSP will store the current stack pointer, RBP will store where the base pointer is, and some registers like RDI, this will store kind of the first argument of some functions like printf and all. And this was discussed in the last session. Okay, next. Yeah, okay, now I'll say what a subroutine is. I told you, in assembly there is no concept of function. So if there was yeah, function call specifically. So if in normal program, like normally in like a C program, you can define another function somewhere outside the main function, and you can call it in the main function. So how this translates into assembly is something called a subroutine call. So in the subroutine call, when you see the assembly of a program, there will be some few subroutine calls. It might not be for the functions which you have given. suppose you call printf, then that will also have the similar thing. Yeah, put the next slide. Yeah, so the subroutine call consists mainly of two of the assembly commands, which is call and ret. So what the uh, call instruction does is it puts the current assembly, it puts the current code into the stack, and yeah, then it goes to there to execute it. It creates another stack frame and it goes there and it executes the assembly code over there. Now then it will be ending with something called a ret instruction. In that instruction, okay, yeah. So the another thing about call is it will also remember where you when like in which line did you jump to call, like in which line you executed call. So that will be stored, and finally after that specific the part of code is executed, it will jump back to where it came from. So it's similar to a function call. Like in a function call, when you reach a function call, it will jump to that function. It will execute the code in the function, and after that, the control flow again goes back into the function call, and again it will continue executing the code below the function call. Similarly, the ret will take you back to where you executed the call instruction from, and it will continue executing the remaining code. Yeah, next. Yeah, so yeah, you saw you had an introduction to stack in the previous lecture, in which stack is a last in first out kind of data structure. And yeah, I'll show you the how that stack looks in GDB. Yeah, next. Okay, yeah, this you can read through this, but yeah, this is what I told. In a subroutine, it'll create a new stack frame and it'll execute it, and then when it comes back, then that stack frame is removed. Yeah, next. Okay, this is what I was telling. In if you see the code in the right hand side, in that in within main function we are calling the square function, and within square function there is again a product function. So how this works in the stack is, initially there is this main function, and it'll have its base pointer and stack pointer, and when it reaches the square, it creates another stack frame on top of that, and the base pointer is changed to there, and yeah, the stack pointer is also changed, and after that again the product function is called, again the base pointer and stack pointer changes, and finally when ret happens, it moves again to the the just be, the base pointer which was assigned just before that stack frame was created, and it again comes back to main. So it's similar to how a function call works. Yeah, but it's in assembly. That's it. Yeah, next. Okay. This is a key concept. Something called buffer overflow. This is one. This is one of the most. I can't say common, but one of the most easiest kind of exploit you can do in to a binary. So what is basically a buffer? So buffer is basically some memory to which you can write. So suppose in C there is no concept of strings. So what you can do is you can assign some memory in which, like, a kind of what do you call it? You can call it an array, but it's basically you can write more than one character and store it over there in that buffer. So basically you can store strings in buffer. But the problem is some of the functions in C, some of the functions in C what their problem is, they won't check the amount of characters which you write into the buffer. So if a function asks you for an input, and you so if a function asks, oh, what is your name, and you'll give your name, and it'll print out the name. Suppose if the program is like that, it some functions doesn't check how many characters you give into the buffer, like in the input. So what happens is, if you write more number of characters than the allocated memory, it will keep on writing the memory in the stack. So what this can cause is, so the uncontrolled writing of the memory will corrupt the stack, and it will mess up all the other instructions if which were present under it. Yeah, next. Okay, this is another example we'll show later. Yeah. Okay. Okay. Yeah, I think I'll just tell about those functions. So one of those functions is called gets function. So in the gets function, there is no place where you can say you have to only get this amount of characters. You just get some input. So it doesn't check for the number of characters. That's one of the unsafe functions. So you can write more number of characters than the allocated memory, and it will keep on overwriting the memory below that. And yeah, it will corrupt your data. So so after that, then there are new functions now, which so there's I think it's fgets or something, in which now there's a new parameter where you can specify only accept these many number of characters, and if you input more than that, then it'll throw an error. Yeah. Okay, these are basically, this is basically how the stack looks like. So yeah, you can see over there, this is how the RAM will be loaded. So in that RAM, on top there will be the kernel code, which is all related to your operating system and all. You can't tamper with it. It is not possible to be tampered. It's a protected part of the memory. And below that is the stack frame which you create while running a program. So if you, yeah, yeah, you can see here that once you so initially there will be the return address of the main function, so which will uh, call back the main function, and it will stop execution. So if there is a buffer under that, and if you, so here the writing of the data is from bottom to top. Yeah. So if you write more data into the buffer, it can override the return address. So that is it will override the address in which it instruction which said to kind of end the program. So if you override that, then the code won't exit properly, and you will get uh, like it won't be executed properly. And sometimes what can happen is, it'll go to something called a segmentation fault, in which you have reached the maximum amount of memory which you could have written, and it just crashes. Yeah, you can read through this. This is some data. Yeah, so the data, there are, these are sections. So BSS data and code. The data section stores the variables, the global variables, and BSS stores global variables which are uninitialized. So in your program, if you define an integer somewhere, but you don't initialize it, those are stored in BSS. And the code section is where your code part is stored. Yeah. Next. Okay. Yeah. So this part of the this part of buffer overflow will be dealt in the next session, where you will see that suppose I'll tell you an example. If in the return address, usually the return address will have the return address of the main function, and you will exit the program. That's how generally a program ends. But what if you buffer overflow and you replace the instruction pointer of the main with something else, some other address which you want to jump to? So if you replace like that, then while the program is ending, then it will return to that address and it will execute some other part of the program. So this can also, we can also yeah wait um, hmm, yeah uh, go back once. Yeah, so in this code you can see there is another function other than the main called spawn shell. So in that spawn shell, it is executing a command to open a terminal. So while the main function is running, if you overwrite the instruction pointer such that it is overwritten with the address of the spawn shell function, it will jump to that function, and then you will and it will open up a terminal. So suppose you have some like a remote server running, so that is basically another computer providing you with some server to work on. And and one of those codes will be asking you for some input, and if you buffer overflow it properly, you can gain access to their system via that remote server. It will open up a shell in their computer and you can mess with it. This is a common type of attack which happens by a binary exploitation. Yeah, next. Yeah, this is what I was telling. Okay, we don't have this program currently, but then yeah, this is it. The if you override the return pointer, then it'll go to that function. Yeah. Now I'll just try to show GDB. Wait, I can't screen share for some reason. I'll just see if I can do anything.
Is it visible?
Yeah, he'll be showing you a demonstration of the GDP. Um, yeah, just first, first, uh, just show the file buffer overflow 1.c. Okay, yeah. This is a simple C program. So in this program, first you are defining a buffer of size 8, and then you are using the gets function to get input into that buffer, and then you're printing out the contents of the buffer. So what is wrong with this program? So first of all, although we have defined a size for the buffer, that is just for the compiler to allocate the memory. That doesn't mean that it will stop even if it's greater, the size of the input is greater than that. And this is because of the gets function that yeah, that doesn't check how many characters you input, and if it exceeds 8 bytes, still it doesn't give you a warning and it just overwrites the memory. So here, when you compile the program itself, you can see a warning saying gets, it'll show a warning while using gets, and it says it's unsafe, and it suggests you to use fgets because of this sole reason. Yeah, run. Compile it with the hyphen with debug info minus g flag minus g flag. Yeah, whatever. Yeah, so now we are in GDB, and we have given so the GDB minus Q flag, that is just to suppress some of the initial messages which is shown by GDB blah blah blah, like it will show some random stuff. So to avoid that, we put the minus Q flag, and then you put the executable which you want to work on. So now it went to GDB, and okay, this is another command which I didn't mention there. It's basically to show the assembly code of the binary which you're working on. So it'll disassemble it and it'll show the assembly code. So you can either write fully disassemble, or you can simply write disas. Just the first 5 letters is also enough, and you can specify the function which you want to disassemble. So this binary will contain the data of those.
Once like is the audio like is he audible like can someone confirm in the chat like
Am I audible? Yeah, okay. I think
you're audible to me but I don't know about the audience like some of them are telling you're not audible.
Not audible. Hmm. I think I'm audible. Right? Yeah, I think it's fine.
Yeah, it's fine, I guess.
Okay, yeah. Yeah, so where was I? Yeah, so you can the binary will contain information of the functions in your program, and you can specifically disassemble the main function. So that is just you can see the assembly code of the main function alone. Also, you can change how this assembly code looks. You can set it to Intel. Set the disassembly flavor. Set disassembly hyphen flavor to there's no space, I think. Fine. And I tab. Yeah. Yeah. Enter.
It's already set in Intel, right? It's fine.
Is- hmm, right. Okay. Never mind about that. So in here you can see the assembly code. So initial part of the assembly code just sets the stack up, and yeah, then it calls the gets function to take the input. Then it takes the input, stores it there, and again it calls the printer function to output the uh, value stored in the buffer. So yeah, so initially we'll see the what is the run command. You can just run it R. Yeah, right. Yeah, fine. Am I audible? Hello.
Yeah, you're audible.
Okay. Yeah. So when you run the program, it asks for the input, and when you input, it takes that input, stores it in the buffer, and displays the output. So yeah, now instead of that, if you give a lot of a string with a very high length, see what happens. Like run it again. See, it returns segmentation fault, which means that it overrode the return pointer and the program didn't execute successfully. Now, uh, I'll also show you how this looks like in the stack. Uh, just do this. Wait.
So like maybe you'll put a breakpoint uh before the printf, right?
Yeah, before the printf. So you just type list. Use just type list enter. Does it do anything? Yeah. So here, because we compiled with the debug flag and we have the source code in the same file, you can use this list command to see the source code. So in this command, now you can set a breakpoint just before printing the buffer. So you can just put B space 5 and you can set a breakpoint over there. Yeah, so we've put a breakpoint there. Now just run the program. Oh, okay, wait. Yeah, run the program. No, wait. Yeah, now we can see the stack. Wait, before that, after running itself, just do Control C and show the stack once before continuing. Just run it again, like set the breakpoint, run it again. Yeah.
Before here hitting the breakpoint.
Yeah. Like when it asks for input, you can just do Control C, go back, show the stack, again do continue and then quit it. Just rerun the program. Just yeah,
Yeah, it asks
Control
to.
C.
I don't know if it works in Windows.
Just do Control C. It doesn't work. That's what it shows.
And it just hits the breakpoint. It's fine. Okay, we show the stack during the
Stack. Yeah, just
like. Okay, we'll
yeah,
just add one more breakpoint before the gets. I guess.
yeah.
Fine.
So what we're doing is we are adding one more breakpoint before we get the value to put in the buffer, and we'll show how the stack looks like before getting the value and after getting the value. Yeah. So now we'll see how the stack looks like. Show the stack. Yeah. So what we did here is we use the examine command. So x by 32 x shows the those much those much memory in the stack uh, under like which. Okay, so here here I think for simplicity they've shown stack growing from down to up, but usually it's actually like up to down. So yeah, wait, print the current memory of RBP also. Yeah. So here we printed the current place where RBP is pointed to. So that is the base of the stack, and it shows the hexadecimal value ending in 15D0. So wait. Okay, yeah, fine. The memory location is EA0. So you can see in the stack above that 5FFEA0 is where the base pointer is, and the value in the base pointer will be the return address of the function, just the value on that base pointer. And yeah, so this is how the stack looks like before we put some value. Now just continue and put the value. Do C, enter, enter few only, don't overflow. Just enter like 3, some value 3, like put 3 and yeah. Yeah. So here you can see that the memory above the RBP where the buffer lies, it is filled with now. It's filled now with hex value. It's something 4141 that corresponds to the hex value of capital A. So the hexadecimal. So you know that all the characters, the alphabets and the numbers have something called an ASCII value. So the ASCII value when so the ASCII value is generally in decimal, and when it's converted to base 16. So so binary is base 2 and base 16 is called hexadecimal, which is used to represent numbers with base 16. So that is basically like in the so it goes from 0 to 9, then A, B, C, D, E, F. So these 16 characters are used to represent hexadecimal numbers. So here 4 1 means okay, so 1 in the ones place means it's just like the value is 1, and in the second place it is a power of 16. So we do 4 into 16. So 64 plus 1. So 41 in hexadecimal is 1 into 16 power 0 plus 4 into 16 power 1. That is 64 plus 1, 65. And 65 is the decimal, that is the normal number on the ASCII value for capital A. So we can see that the part of the buffer in the stack is now filled with the values A. Now, yeah, now just rerun this and put more A's. Can you do that? Hello, am I audible?
Yeah, you're audible.
Yeah, yeah. So see here, now when we put more number of A's, it already overrode the space 8 byte space allocated to the buffer, and it also overrode the part of RIP. Okay, the instruction pointer basically, which was in RBP, and now if you run it, it'll show error. It'll show that yeah. Now the RBP is overwritten. Yeah, and it okay fine. Yeah, it didn't check fault because we didn't override more, but then it didn't properly execute. Like um if there was some code there, it would not have run. Yeah, just see the stack now. Okay, yeah, you can't do anything. Yeah. So if you put more number of A's, then it'll do something called segmentation fault. And wait. Okay. Yeah, I think this is it for the session. Actually, this is very basic, and yeah, I was not able to show you more. Oh, wait, let me see if this. Yeah, just also okay, fine. Yeah, yeah. I think that's it. Fine. That's it. No, is there any more? Like you can test GDB yourself. Like write a C program, compile it, and run it like this, and you can see for yourself how it works. Like you can try out the other commands which I showed before. You can go through the recording, pause it, and try those commands. Um, yeah, I think okay. I'll try to make a document in which I'll show some examples for you to try out. I'll since I was not able to present, I'll just give the source code and what I'll be doing with GDB. I'll put that in a document and I'll try to share it like before the next session. Next session will be on Tuesday and it'll cover buffer overflow in detail and it'll teach more concepts involved in binary exploitation. Fine, I hope what I explained was understandable today. If
Uh,
you guys have any
like,
doubts,
can
you
you
can raise
just
your hands and
explain,
ask.
just like summarize once the people asking us to start from the again. So just summarize it once, the last part, like the example part, I guess.
Hello. If you guys have any doubts or you don't understand anything, you can raise your hands. Q&A.
Guys, if you have any doubts, you can just raise your hands. We'll unmute and you can ask your doubts.
If you guys have any doubts, you can raise your hand. Okay, I guess you guys don't have any doubts. So, if you are not clear with anything I explained, just go through the recording once. Even if it's not clear after that, then you can put it in Teams in the general channel. It's not only for posting the links or any other queries. You can also ask concept specific doubts over there or in the WhatsApp channel. We'll clear it over there. And I had shared how to install WSL in the Teams. If it was if there is any problem with that also, you can let me know. But then sometimes it might not work. Windows will have some issues and it won't install the thing from the Microsoft Store. In that case, it's fine. Uh, you can still you can try to use you can try and find out how to use GDB in Windows itself. You can use it over there, or you can try to set up a something called a VM, a virtual machine, by downloading VirtualBox. As that's another option, but all those are complex options. So what you have to do is, if you're trying to do any of those, you have to go to the internet. They'll have the official site will have proper documentation on how to do it, and you have to follow that strictly, and you have to be careful. Yeah, yeah, you can ask. Hello, hello. Hello, you have any doubts? Shri? Hello? Hello? Yeah, if you guys don't have any doubts, then you can leave. Actually, it's fine. The session is done. Wait. I'll end the meeting. Don't leave. Wait, let me check Q&A. The slides will be shared later. Don't worry. For now, please adjust with the recordings. Like, I think they'll share the slides together or something. With the managing the summer school management is like sorting it out. So don't worry about the slides. Just go through the recording, pause wherever is required, and read from there. That's what you can do for now. And the slides will be shared soon. Till that, please go through the recording. Okay. Okay then. Thank you for attending the session. Next session will be on Tuesday, the same time, 3 to 5. That will cover more depth, buffer overflow, and some new concepts. Uh, stick onto that. And if any of your friends or like if anyone was not able to start listening from the beginning, go through today's recording. It will be available after the meeting ends. Yeah, that's it. Okay.